given me opportunity to give a talk here, and it's my pleasure to meet many people here. So today I'm going to talk about graph decomposition. And actually this is joint work with Professor Kostachka and Professor West, who are the professor at University of Illinois at Urbana-Champaign. And Hawei Wu is a student of Doug West, and Xuding Zhu is Chinese, and he is a colloquium speaker in April. So. Okay, so my today's talk consists of this way. So first I'm going to talk about, I'm going to explain about graph decomposition, and then I'm going to explain the previous result and then our result, and then I'm going to introduce the 9-dragon conjecture. So you can see why the name is 9-dragon conjecture. So first, graph decomposition is a decomposition of edge set. So you can see the red color edge and blue color edge. So and then here we have a question if the Q3 can be decomposed into forest and matching. But if you decompose it this way, then you can see the 4 match, right? Then the remaining edge has a cycle, right? So, this has a cycle. So this way, we cannot decompose into forest and matching. So maybe this approach is not good, so we may try another way, this way. But still, we can see a cycle. So in general, Q3 cannot have such decomposition because each vertex has at most one edge in the matching, right? So the remaining vertex degree is at least 2 for every vertex. So it has a cycle. So, but Q3 has a decomposition with forest, and then, the blue color edges of forest, and then a cycle, a path, the maximum degree 2. So Q3 has this way, have decomposition this way. The decomposition with forest and maximum degree 2. So now we consider another case. We have a bipartite K26, and then we have a question if this graph have decomposition with a forest and a subgraph of maximum degree 2. So how do you think? So okay, red color edge is a subgraph of maximum degree 2. Then the remaining edge has a cycle, right? So this way, we cannot have such decomposition. Also, in general, because maximum degree is at most 2 for each vertex, and maximum degree at most 2 at vertex x and y. So actually, at most 4 edges participate in the subgraph. So the remaining graph must have a cycle in this case. So we don't have such a decomposition. But if you increase the maximum degree to 3, then we can have such decomposition. The blue color edge is a forest, and the red is a subgraph of maximum degree 3. So in general, if we allow large degree in the subgraph, D, if we decompose graph into forest and subgraph D, and then if we allow the maximum degree, if we allow the large maximum degree for D, then we have more chance. So this is a general pattern. So the history of this research of this direction is as follows. Okay, people try to decompose a planar graph into forest and a subgraph of maximum degree. I mean, the D-bounded graph is subgraph of maximum degree D. So if Gauss is at least 9, then you can decompose planar graph in forest and maximum degree and forest and subgraph of maximum degree 1. And then later, last year, Wang and Zhang, they proved, and if maximum degree is 8, then we have such decomposition. And actually, this bound is tight. It's sharp. And if maximum degree, if we allow maximum degree 2, then and then larger class of planar graph have such decomposition. Also, this result, I mean, if we allow maximum degree 2, then the condition Gauss 6 is also tight. And then I think I'm not sure if this is tight or not. Yeah. This is actually this is motivation. This is a game coloring number. Game coloring number. Actually, the motivation of this study is to obtain the game chromatic number. Game chromatic coloring is okay. Sang-il and I try to color each other. So each time I color one vertex, and also next time Sang-il color another vertex. So my goal is I try to use a small number of color. Sang-il is bad person, so he tried to push me. Yeah, try to push me to many colors. So game chromatic number is, so maybe I have some, I have some algorithm to guarantee small number of colors. So if we have such decomposition, then people find some algorithm, then we have the small upper bound. Actually, this type of research it came from the game coloring number. So lesson 3, this is another direction. I mean, these 4 people conjectured in 2005, and what their conjecture is planar graph can be decomposed into 3 forests, and then the one forest has a maximum degree 4. And then he showed that this conjecture is true. Actually, both papers appeared in JHTV. And then, okay, this is application, what you asked. I mean, the game color chromatic number as upper bound has this way. If graph is decomposed into G1 and G2, and then game chromatic as upper bound this way, and if G1 is 3, then people calculate the small upper bound. So if the second graph has a small maximum degree, then we have a small number of upper bound.
So the first theorem by Zhu, we don't need any condition on G1 and G2? Just
G1, G2, G1 is for no condition. So from this paper, people try to decompose decomposed into G1, G2, and then G2 has a small maximum degree. That's why people have this type of result. And the game chromatic number is we have some different explanations, so let me skip. So in this direction, so let me introduce what's the meaning of the sparse graph. Sparse graph is, typically when people study with the Gauss condition, but people try to find more general results. In this case, people approach with the maximum average degree. Then what is the maximum average degree? It's just the ratio between number of vertex and number of edge. And then using this formula, if we have some result about with the maximum average degree, then it implies some result about Gauss condition. So in general, the result with the maximum average degree is more general setting. So again, our goal is, so what is the sharp condition to have such decomposition? Okay, let me explain the relationship between maximum average degree and Gauss in the next slide. Okay, some people who are not familiar with the relationship between maximum average degree Gauss. Okay.
Can you explain the definition
Gauss?
first?
Gauss is the smallest cycle, size of smallest cycle. So I think everybody knows this inequality, right? Equality. And then it should be inequality. So every phase has satisfied this inequality. So because the G divided by G, we divide by with the G both sides, right? And then using Euler formula, then if we simplify, we have this way. And then this one is maximum average degree. So here's we have a situation. If Gauss is 6, so if you plug in 6 here, then this value becomes 3. So okay. So one type of result is okay, if Gauss is at least 6, then you have such decomposition. Then maybe later, if you show, okay, if maximum average degree is less than 3, and then we have such decomposition. Then second result is more general result than first result. So for instance, here, okay, K5 is not planar graph. So if you subdivide each edge of K5, then it's not subgraph. It's not planar graph. But maximum average degree is smaller than 3. So this graph has a decomposition. Here, this result is for only planar graph. So we want to extend our result for more general graph. So as you can see, subdivision of K5 is not planar graph, but still it has such decomposition. So in this direction, lesson 3, there's result like this. If maximum average degree is less than this way, then graph decomposes into forest and subgraph H, and maximum degree H is at most D. But maybe you are not happy with this result because this value is too complicated. So we don't want to see this value anymore, right? So now question is, what is the sharp condition to have such decomposition? I mean, is it sharp, or can you upgrade more? Can you improve more? So here's an example. I mean, the K2, the bipartite graph K2, 2D plus 2. Then if this graph have such a decomposition, I mean the forest and a subgraph, then vertex X and Y, they have at most D edge, incident D edge. Then how many edges do they use? Just at most, they use at most 2D edges. So remaining edge is this way. But number of vertex is also 2D plus 4. So it must have a cycle, right? So this graph cannot have such a decomposition. So this could be a sharp count example. And then the maximum average degree of this graph is this one. So our natural guess is, maybe our hope is, okay, this boundary is sharp. So question is, this boundary sharp? But in this paper, they said they obtained this value. I mean, there's no more hope to improve this value. They said they obtained this value really best possible way. They use discharging technique, and then they said, typically discharging technique is very complicated, and they said, and also several very clever people participate in this paper, and they say, we did, in the discharging technique, this is best possible way. So for some time, we are not sure this value, if this value is sharp. To do this, we need to find another counterexample. Or maybe this value is sharp. So what is your guess? Which way do you want to try? Both ways.
Because there exist other counters, a non-isomorphic counterexample with the same value as this 2 plus 2.
Yes, there's another. I mean, the subdivision of complete graph. Yes. So I mean, this is question. I mean, if this value is sharp, and then there's positive result in this direction, and then these people, I mean, the French people and shooting Jew, they show that when D is 1 and 2, this bound is sharp. I mean, they are able to show when D is 1 and 2, they are able to show this bound is sharp. And then also their result imply the second graph H is also forest. So they show more stronger result. So what is next?
I mean, if D is 1 or 2,
yeah,
then either pass or cycle.
Right. So when D is 1, it means forest or matching. When D is 2, forest or pass. So our result is, okay, that bound is sharp for every D. And then we have a more stronger result. When D is n most 6, then actually both graph F and H are forest. And the more stronger result, when D is 2, and then second graph also is just union of this type of edge. Or just this. H is looks like just this way. I mean, each component has at most 2 edges. I mean, the previous result in the second graph could be this way, long path, right? But second graph is just each component has at most 2 edges. Okay, this is the meaning. I mean, like this red color edge is the second graph H. And then the remaining edge is forest. And then relationship with Gauss condition. Actually, it implies the previous best possible result. I mean, the previous best possible result is, so if the maximum degree is 1, then Gauss 8 is best possible. And if maximum degree is 2, then Gauss 6 is best possible. Then also our maximum average degree condition also imply this Gauss condition. I mean, when D is 1, it means 8 over 3. When D is 2, is 3. So it completes this type of problem for small value D.
And this is because the K2 G2 plus 2
Yeah, right.
is planar. And so in some sense it's
Yeah, yes, yeah. Yeah, it makes sense. So now what is the 9-dragon tree? Is the 9-dragon tree, okay, let me explain first what is this conjecture. There's famous theorem by Nash-Williams. I mean, if G has, graph H has, if graph G has at most this edge for any subgraph, then G can decompose into K forest. So if you call this value by arboricity, then number of forest is the ceiling of arboricity. So here is question by Professor Shooting Zhu is, what happens if arboricity is just barely bigger than 2, but still we need 3 forests, right? I mean, the idea is if the value is 2999 or 2001, even though both graphs need 3 forests to have decomposition, but there should be something difference, right, between 2 graphs. So what is the difference? So that was question. And then they conjecture this way. So if arboricity has this inequality, then graph can be decomposed into K forest, and the last forest has a small maximum degree. So that,
why is it 9-dragon?
yeah, so 9-dragon is I think that it's just just no. I think just it came from Chinese character. I mean that Shudingju school is the Sun Yat-sen University in Kaohsiung, in Taiwan. And then, yeah, there's a small mountain, and on the top mountain there's a tree. But the tree has so many branches, and some branch has already planted on the ground already. So it is tree, but it looks like it's not tree anymore. I mean, because it has a lot of cycle. So actually, I think the name of tree is a 9-dragon tree. Actually, the many graph theorists visited this tree, including me. So whenever Shudingju invites some people to Taiwan, he always takes people to this tree. So in observe of this tree, the people decide, okay, let's call it 9-dragon conjecture. So regarding this conjecture, so our result, let me explain our result. So by these people, what they show is 9-dragon conjecture is true when K is 1 and these 1 and 2. And then our result imply 9-dragon conjecture. Okay, our result is not same type of result of 9-dragon conjecture, a little weak version of 9-dragon conjecture. Because our last graph is not tree. It's not forest. But when this exactly K plus 1, then we show that the 9-dragon conjecture is true for every K. Also, when these m most 6, then our result implies the 9-dragon conjecture is true. So the remaining case is when d is at least 7, or also when k is greater or equal to than 2, then those cases are open. So maybe so far, any question? So whenever we present this paper, always we worried, I mean, because there are so many numbers and so many inequality. So people get tired quickly. So next.
So this conjecture doesn't imply the previous result when K is 1 equal.
Yeah, it's not same previous result. Actually, this conjecture is maybe more general. Okay, another case is, I think still Shudingju tried to modify this conjecture. He guessed, okay, this is right direction. I mean, this is appropriate direction for research. So key idea is we introduce this function, and then so for every subgraph A, if this function is non-negative, then in that case we show that graph have such decomposition, and also the discharging technique is involved. So when K is 1, so if we plug in K is 1, then it's 2 K plus 1. So if we simplify this, then you have this value. Actually, this is this form is nothing new, just for the maximum average degree. Then if you write down on the on one line instead of a ratio, then you have this form. But this form has actually more general case. And then from now, so slide will become more complicated. So please be patient. So, okay, this case is what we want to show. I mean, this case is actually what we want to show. And this is more general case, and this is intermediate case. Actually, we show this intermediate case satisfy the condition. I mean, if you satisfy this case, then you have such decomposition. So what is the relationship of these three cases? If graph satisfies this inequality, it means it satisfies KD sparse, also it satisfies maximum average degree condition. So it means if we show this theorem, okay, when graph is KD sparse, then we have such decomposition. Then if we show this theorem, then it implies this result. The reason is this condition implies KD sparse. So we use induction, and then it becomes more complicated to use induction conveniently. So we introduce this complicated function. The main purpose, the advantage of this complicated function is this helps when you use induction. I mean, even the form becomes complicated, but induction argument becomes simpler. So we show if this function is non-negative for every A, every subset A, then we have such decomposition.
What is F bound?
This one. So I think that our original case is every f of v is d. That's our original case. So when f of v is d, then these complicated functions become simplified this way. This is our original function. And then the result is almost sharp because we have this construction. And this construction has no such decomposition, but the beta value is just -1, just barely below 0. So this is why we say this is almost sharp. And then maybe it's better to skip this second. And the third one, I mean that if D is at most 6, then we have G decomposed into two forests, and one forest has a maximum degree of D. Then so we use discharging here, and then our minimum counting example has satisfied this condition. I mean, if G is adjacent to two vertex, then this vertex degree of this vertex should be very high. Also, every neighbor every 3 vertex has a very high degree neighbor. Because always discharging is so if you have small degree, then it should have a very high degree in the neighbor, and then in the high degree vertex can distribute their charge to small degree. So this is rule, and then actually this is end of our slide.
So you only have 2 rules.
2 rules. But in the argument, I mean, the key point is very. It takes some. Always this part is always most difficult case because we have this type of strong result condition. Then we don't need to complicate the discharging rule. I mean, if we have a weak result in this part, then we need to have a lot of very complicated discharging rule. And then, so as a summary of this paper is, originally we start with discharging technique like this. And actually we proved that later we proved the theorem using this function. But this one does not use discharging error. And then recently another paper gets similar result like this, but weaker than this, but they use Metroid theorem. So it has very several approach. Okay, this is end of my talk. Thank you.